Hi everyone, really nice to see you. My name's Garry Clawson and I'm a third year student, and my talk today is around blockchain. So what's this thing called blockchain? It's a topic that has an underlying current to it. Some people hear it, there's misconceptions, there's misunderstandings, and hopefully today one of the things that I'll be doing is just giving some clarity around what blockchain is, how it's useful, some of the history towards that, some of the exciting things that have happened, some of the not so exciting things that have happened, and just to give you a bit of an adventure through what the whole blockchain journey. So my name's Garry Clawson. I'm a third year student in computer science at the University of Lincoln. I'm a mature student, so studying is something that's becoming new to me, but it's been really exciting, and this journey of computer science has been really great. You can see my GitLab and GitHub links there, so please feel free to check any of those things out. So what are we going to cover today? So I'm really excited about this talk. It's a talk that I've been wanting to give for many months really, and it's a talk that we could have really done in year one, year two, or whatnot, but we're going to try and cover some things today, and we've got some really exciting things. So we've got, what are transactions in a blockchain? What's mining? What's that all about? Why is there 20 different Bitcoins? Why is there so many forks? How do blocks propagate? What's that all about? And what does it mean by propagation? What's a hash? Why do we have a hash war? And why are people arguing over these things that some can see as not very important, but ultimately to the scheme of things, they're super important? And also, what's a node and how does a user play a part in the blockchain? And then we're going to end it all. We're going to feed some chickens. We're going to use second layer technology, and we're going to give a demonstration of what this is all about. So I hope that's going to be fun. So the approach today, I'm going to break this session down into three components. I'm going to break it down into a mind, body, and spirit. So what do I mean by that? So from a mind perspective, what do we mean by blockchain? Are they new? What is a block? How do you link it into a chain? What's a transaction? How do transactions relate to blocks? How do you gain consensus? How does one block be approved and another not? And what happens if something goes wrong? So we're going to be talking about the software sort of side of things. And then we're going to move on and take a tangent, and we're going to flip over and we're going to look at the body of the blockchain. And we're going to talk about mining, and we're going to talk about the network and how they physically operate, what the role a user plays in. Can you cut a blockchain in half? Can blockchain scale? And how would you, if you wanted to scale a blockchain, what are the different options of doing that? And then we're going to go look at the spirit as the final part of this trio. So is it possible to duplicate a blockchain? What does a successful blockchain look like? Can they grow old? Does that even make sense? Is a question. Can two of the same blockchains exist side by side simultaneously? And importantly, who decides what blockchain is the right blockchain? So where do we start? Well, there's so much history to blockchain technology that it's very difficult to drive down. If you were to drive down at the very beginning, you'd be stuck in the 60s talking about cryptography and all this sort of stuff through the 70s. So what we're going to start with today is we're going to start with the very beginnings of the most popular blockchain, the most well-known blockchain, which is the blockchain around Bitcoin. And we have here the Satoshi Nakamoto, sort of an anonymous developer, built the Bitcoin blockchain, and this was in 2008, October. It went on the Metoid cryptography mailing threads and just dropped this note in and said, guys, come along and have a look at this. So this is where we're going to start. And this is important because blockchain, Bitcoin as the first blockchain is the blockchain that we're going to use as a datum throughout this whole discussion. There are many different blockchains, and they all do slightly different things. Some blockchains run on top of other blockchains. Some blockchains run to the side. Some blockchains rely on mining power from a sister blockchain in shared mining. So there's a whole different scenario of this. But the best place to start is on the Bitcoin blockchain, because then we can jump off from that. So a question that a lot of people wonder is, what exactly do blockchains solve? What's the purpose of a blockchain? Well, as Satoshi Nakamoto identified in the white paper, in the Bitcoin white paper, blockchain is here to solve a problem called the double spending problem. And this is solved using a peer-to-peer network. And the implementation of that peer-to-peer network is via timestamps and hashing together into a chain of hashed proof work. So that all sounds sort of crazy, and we're going to go look and see what is hashing, and we're going to have a demonstration. We recognize peer-to-peer because we sort of have Napster in the back of our minds, and we think about how networks are developed. But then we think about how do blocks form so that you can't unwind them? How do you not take a block, copy it, and send it somewhere else? So, and this is really the problem of double spending. What's to stop something digital being copied and then sent somewhere else? And this is the whole problem of what blockchains were really here to solve. And what that provides is in itself is digital scarcity. So scarcity from a digital perspective hasn't really been possible until blockchains were really developed. And what that allows is certain different things to occur. One of them is transactions and value-based messages. Others are tokens that exist on a blockchain that don't exist anywhere else, that have inherent value in themselves because those tokens they represent something, or they represent some artwork in real life, and you can then transact that in and around. So this is the type of problem that at the moment blockchains are really focused on resolving. But as blockchains develop and grow, they'll certainly be looking at second and third layer activities and how you can take all the issues with the current base layer blockchains and try and mitigate them. So what does a block look like? Well, on the right, we've got a picture of a block here, and this is entitled block 10, block 11, block 12. And we've got 4 or 5 items in here. We've got a previous hash of a block. So we've got a hash of this whole thing here. We've got a timestamp. And a timestamp's important because how do you manage time on a global network in this sense? Well, the way blockchain and certainly Bitcoin manages this is by having 2-hour flexibility. So if a block is mined, even if it's successfully mined, but it's not within 2 hours of the average time of previous blocks, then it will not get submitted. And here we can see we've got a transaction route, and this is built for using something called a Merkle tree, and we've got transactions built into a hash, and then hashed up here. So this is just going to be one long string of text. And then we've got a nonce. Now the nonce plays an important role within a block. The nonce is something that you would increment as you're mining, and we're going to be talking about that a little bit later. But you can see here we built a block of a previous block here, the hash. We've got a timestamp. We've got all of the transactions, and then we've got something in increments, and then we hash all of this, and then this goes into this following block. In this link here, this is the actual chaining. So okay, so that's great. But how do you make sure that block 12 doesn't come before block 10, or how do you not duplicate block 12 and or block 11 and have 2 block 11s? Well, this is where we begin the topic of mining and work. So the way that a blockchain in this sense is secured is via CPU cycles. And in the very beginning, it was always envisaged that CPU cycles would be used on a personal or independent basis. So I would have a machine, it would be running a node, and I would be running my Bitcoin node CPU cycles to secure the network. But things have developed significantly, and there's a great history behind this. Characters involved, Art Force is a character, and moved CPU mining into the GPU realm, and now GPU into ASICs, and now you get ASICs farms, and I'll be showing you some of those things as we move on. So we've got a sense of what a blockchain sort of is. It's really a timestamp server full of hashes of previous things, full of hashes of previous blocks. But how is that then sort of secured, and what's that sort of look like? Well, one of the things we're trying to secure is the transactions. So blocks, that's what blocks contain. So a block contains a series of transactions, and depending on the size of a block could be 1 megabit, it could be 200, depending on what chain you're on. It depends how many transactions you can fit in. And currently, over a period of 24 hours, the Bitcoin blockchain can tolerate about 300,000 transactions. You might get about 2,000 transactions a block. So you can sense that there's about a megabit of size, and that propagates about every 10 minutes. But an important thing, really, that is a good place to start is there's no such thing as a Bitcoin. in itself. All you have is just a series of inputs and outputs. And it's like saying, so that may sound strange. So if I give an analogy, if I have some change in my pocket, £4.62, say, and I look at this and I say, look, there's £4.62 here. There isn't this thing that's £4.62. I can't go and point at a £4.62. It's just a collection of stuff that translates into £4.62 of this sort of value. And it's similar, or it's exactly the same rather, with Bitcoin and the blockchain that Bitcoin operates on, with these series of inputs and outputs. And these are called unspent transaction outputs. And this really begins the topic of how do we manage these transactions? How do we sign them? What are keys and what are cryptography? What's cryptography, and how is that important to be secure when you're operating on those on that type of level? Now, transactions in themselves are quite simple. In the sense that what you're doing is you're spending a transaction that you currently have. So if I was to make a transaction from Alice has £5. She would like to make a transaction to Bob for £4.20. Alice would have a £5 note because Alice has a single UTXO in her wallet. Sends that to Bob. Bob obviously only needs £4.20. So what happens there is there's something called change. And you will get change back. So in every Bitcoin transaction, there is always a minimum of 2 outputs. And there's an output to the spender, and then there's an output back, which is to you as change. And we can see this on the next slide. So in a sense here, what we have is we have a sender, and the sender becomes the receiver's input. So this change section that's happening here, we can see we've got an input, and then as we send a transaction, we have the change that's sent back to us. And then this propagates, and what we'll have here is we'll have another transaction. So now Bob has a transaction and I'd like to send it to Carol. That transaction is Bob's unspent transaction output, and then it propagates to Carol. They also may get change. And you can see here, this would translate all the way through, and you would get this large propagation of all these inputs and outputs through. So you may be asking, okay, that I can understand that. That's great. That just seems to be passing on messages. But what we'd need to understand from a privacy perspective is that any change addresses will always go back to the same address, or they do now, the same address that you've currently sent your Bitcoin or whatnot from. And the reason that's done is because historically you'd have to define your own change address. A lot of people wouldn't do that. They would forget because you'd have to do it manually. And then that becomes what's called a fee to the miners. And the miners would then take that. And if you've got £10 and you're only paying for something that's 20 pence, then suddenly this fee, you've lost £9.80, you've lost a large chunk. And this happens a lot. And people would have to go cap in hand to the miners and ask for their transactions back. Generally, that would always happen. So transactions are pretty important from this basis. There was a story about as we look at transactions and we look at how wallets are created. I know Ben Williams did a great talk on randomness a few days ago, and it was only in 2015, 16, where there was one wallet and it was using, I think, random.org as its random number generator. And suddenly you had all these random numbers that weren't necessarily that random. And a white hat sort of hacker had to go along and try and siphon up all these coins. And I think there was about 1,000 Bitcoin in the end that had to be given back to their rightful owners as long as they could sign the right keys. So there's a lot of background with regards to that type of stuff, and there's lots of interesting stories as we go along and think about what these transactions are. So we've got a sense of, or a very, very sort of high level sense of what sort of a transaction is, what a block is, what a transaction fits in a block. But then we think about, well, how do we make sure that everybody or every participant on the network understands consensus? And there are many different forms of consensus. Bitcoin uses something called proof of work, and the proof of work is the proof of the CPU cycles. Ethereum, another very well-known blockchain, is transitioning to something called proof of stake, where you would stake a value of your particular network token, in this instance Ethereum. There would be 32 Ethereum staked, and if you were found to be mistreating the network in some way by not being honest, then you would lose your stake. And so that sort of provides an incentive mechanism. And the incentive there is there's concern around energy usage and things like this, and I'll touch upon that later. But an important aspect to understand is that consensus rules are followed by miners, and we're going to talk a bit more about miners later. But they are enforced by nodes. Now, this is a contentious thing to say. It doesn't mean that much to maybe many people, but many would not agree with this statement, and actually it was the basis for a significant chain fork in 2015 to 2017. The idea being that there's different interpretations between white papers and things about what exactly a node is. Should a full node be a mining node? If it's not mining, is it of any use? Because it's not ordering transactions, and so on. So there's a lot of sort of talk around that. But this topic then leads on to things called attack vectors. And if there's only 3 or 4 people mining, then suddenly 51% attacks or Sybil attacks, where you could be surrounded by cheating nodes, become a lot more problematic. I think it was 2016, there was a lot of concern around what's called simplified payment verification, which was where a user would have an Android wallet, and they would be transacting, but because they wouldn't necessarily have their own node, they would be trusting another node, and you would then have to place faith in that node to do the right thing. And if too many people place too much faith in those nodes, or it's too heavily used, and that node was then surrounded by something that it wasn't meant to be seeing, then such as fake nodes, or nodes that are feeding it incorrect information, then suddenly you can find yourself on a different chain, and you wouldn't even know about it. So consensus here is all about making sure that every node sees all the other information from all the other nodes in the same way, and ensuring that the miners not only follow the consensus, but that the independent nodes enforce that consensus as well. So what if something goes wrong? Well, let me tell you, everything goes wrong all of the time. You'd think it's this thing that goes on, that runs sweetly, but actually it isn't. And there's a lot of CVEs, and you can find these, it's completely open. And these, if something goes wrong, then you can lead to chain forks or denial of service attacks, or even inflation bugs. And the most critical inflation bug was actually in March 2013, where I think 128 billion Bitcoin were accidentally created out of thin air. And that was a real problem, because what happened there was that had to be rolled back. There was a new implementation, version 0.8, that was developed that used something called, I think, Level or Berkeley DB, a sort of backend database, and then there was a transition to Level DB. And what I found, there was some sort of check or something that hadn't gone quite right. And when you had half the network using 0.7, version 0.7, and half the network using 0.8, then suddenly somebody was seeing half of something, and the other guys were seeing something different. But this really then begins to touch on the topic of community and BIPs, Bitcoin improvement proposals, and then also importantly how upgrades are approved. And so this is really a key topic, because the approval of upgrades is, or can be, really slow. But that slowness and that wait really adds benefit, and it's certainly not done in an isolated way at all. More recent bugs that were seen, there was trying to do some improvements on the Bitcoin wallets. I think they want to take 600 microseconds out of something, and accidentally some sort of overflow, and that caused again some more inflation, and that had to be unwound. But it's really great to see the community come together, because these things get tackled very, very quickly. As soon as someone sees something, you can be sure that 3 or 4 hours later that something's being done, and all the mining pools and all the nodes are being communicated with. So when something goes wrong, what you really need is a strong community around you to help with that. And community is a key theme that I need you to keep your mind on as we talk about blockchains, and maybe the spirit of blockchains later. So if we've spoken a little about the mind of a blockchain, we've touched on very briefly, what a block is, maybe what a transaction is with its inputs and outputs and unspent transaction outputs. We talked about maybe a little bit about consensus. But let's now look at the body of a blockchain. And this is a small Bitcoin mining farm. But the important thing about this is we think about energy usage. This sounds great. This is like cybernetic drones flying from 2,000 to 248 coming out to get you. But this particular mining farm is actually in a container, and this is in the oil basin in Texas. And what these guys do is they use flare gas from these basins to mine for Bitcoin. And what's that doing is that all that wasted energy is then being used to secure the network in that sense. So that's getting a lot more positively used in that way. So all that humming in the background, they were ASICs, they were mines. That was a very small mining farm in containers that you can just ship anywhere in the world at a minute's notice, and you can get somebody mining for you. EDF and these guys, I think, have begun to think about how they use this on their network, because otherwise you've got a lot of energy that just goes into the ground or electricity, and they can use that to do other things. But what exactly is this process of mining? Well, mining is the process of expending CPU cycles to prove that some type of work has been done. And I've got a small video on the right here, and this is a chap called Ken Sheriff. He's great on a lot of computer architectures. And here he is mining Bitcoin by hand. And he's going to do one round of hashing, and it takes him 16 minutes, 45 seconds. So a block requires 128. And if it's a large block, it requires 192 rounds. And so you can imagine Bitcoin mining by hand is extremely intensive, and it's not something that's ever going to win you a block. To be fair, that's not going to happen. But the work the CPU does should have no inherent value. Now, that's again is a very contentious statement, and it's really the basis for various alternative coins, altcoins, and the perception that Bitcoin mining wastes energy when it could be doing something like folding proteins or something useful with all those CPU cycles. Now, the key thing to understand here is that if the very act of mining and creating hashes has value in itself, then that value detracts from the value of the network, and people would then begin to mine for the sake of creating those hashes, regardless of what state the network was in. And if the network was failing, or there'd been a fork and something had gone wrong, they would still be mining. So suddenly, what you've got there is a bit of game theory that comes into play, and you've got incentives and motivations. So having value in the very act of doing something in itself takes away value from the other act that it's supposed to be securing the network. So it's a bit of an odd way to think about it, but the less value those hashes have, apart from finding or proving CPU cycles, proof of work, actually the better. The proof of work that's done on the Bitcoin blockchain is using something called SHA-256, and this is a function that you can take an input of any length and it will digest it to a smaller sort of length. But the thing is that from the input, you can never guess the output. And the idea is that a proof of work should be something that's hard to do, but really easy to verify. And the outcome of mining is really about the ordering of transactions within the blocks. So you're mining these blocks, and we're going to see a little bit more about that now. We'll just see Ken do a little bit with his pen and paper.
Of the SHA-256, we start with 8 inputs: A, B, C, D, E, F, G, H. For the first round, these are constants provided by the NSA. No joke. So our first step is going to be convert these to binary, which is straightforward but a little tedious. So we'll start with ABC. 6 is 0, 1, 1, 0, 1, 0, 1, 0,
okay.
0, 0, 0.
So you can get the sense of what's happening here, and this has all obviously been subcontracted to CPUs, and a human is obviously by hand is no good at doing this. So how does mining work? So mining uses, as previously mentioned, this SHA-256 hash, and it could have used something like SHA-512 or something like this, but it's used SHA-256. It actually uses it twice. It's called double SHA-256. And what it does, as I think we mentioned before, it's the hash of the previous block contents and the nonce. So what do those block contents look like? Well, we did see a little bit. We know it's got transactions, and we've got transactions along here. And then we can see in this particular block, it's got 63. This is a block on the blockchain that's currently there, and we're going to be mining it in a second. So that's quite good. So we've got a version number. So this version number allows people to signal within the network, and we'll be seeing this a bit later as well, what they approve of and what they don't approve of. So there could be a proposal, and the version number is something that's used to support that proposal or not support the proposal. So you can then build up an idea of all the miners on the network, who is supportive of what particular proposal or not. And I'll show you how that works in a moment. And here we've got the previous block of the hash, and it's reversed. And I was looking at this yesterday, and there's sort of like a little or a big endian sort of thing that goes on here, and I'm not 100% sure what goes on. And it's the same with the Merkle root of the transactions. This is also reversed as well. And then we've got a timestamp. This timestamp is in hex, and it's year, day, month, and then hour, minute, second. And then we've also got bits, and then we've also got the nonce, which is incremented around here. And so we can see here, this would actually start at 1. So I don't see how many zeros there are, but we could see we're maybe at 487 million there. So there would have been 487 increments as this block was mined to achieve this block hash. So how exactly does this all come together? Well, and what are you trying to find? Well, what we're trying to find when you're mining is these leading zeros here. So that sounds a little bit odd. So when people say, oh, I'm Bitcoin mining and I'm trying to solve this hard problem, and you see a lot in the media, that doesn't necessarily make a lot of sense, because the problem isn't necessarily hard. There's no hard problem to solve. What you're trying to do is you're trying to do something that you just cannot, without brute forcing, have an output that you can guess from. And what miners do is they take all of this and they'll hash this twice using SHA-256 as mentioned. And once with hashes, if you change the input even so slightly, the output will be completely different. And so this particular block would have started at 1. They would have hashed this whole thing, and then they would have checked the block hash for these leading zeros. And these leading zeros, the more of them that's required, the more difficult it is to do. And that's about network difficulty. And network difficulty changes with the more miners that are on there. And we'll talk about that in a second. A successful hash is one that starts with enough zeros. And the only way you're going to find out you've got enough zeros is by brute forcing through every single hash that you can sort of get your hands on. If you find a hash, then you win, or you achieve the block reward. And so this is called mining. So when someone has mined the block, i.e. found these leading zeros hashes, you then receive the block reward, which is in the form of Bitcoin. It started at 50 Bitcoin. It then halves every 4 years, 25, 12.5, 6.25 now, within each block. And each block takes about 10 minutes to resolve. And and we'll speak about that on the next slide. So what exactly does this look like? Well, what we've got here, so credit to Turinut, so about this very small Bitcoin mining Python code. So I've changed this a little bit here. So I've added a previous block in, which is here. We've added the Merkle root in, which is here, which is the hash of all the transactions. We've got the time, but this is the hex value of the time, or epoch time. And then we've got value in the bits field. And what we've got here is we've got a nonce, and this is this nonce here. And what I've done is I've started it a little bit later so that it doesn't take too long to mine this particular block. Because this block has already been mined, we already know what the inputs were to successfully mine it. Now, it's crazy to me to think that there have only been 650, say, 1,000 blocks that have been mined, and this is since 2009, say. And it's funny that all the hash and all the power and energy that went in, and the only thing that was sort of successful was these very small 650,000 outputs that are probably 20 digits sort of long, and they were the sort of things that everyone was trying to fight over. So that's quite funny. So we're just going to try and mine this block. So I think if we start counting here, this takes about 10 seconds, and it's going to come to an end very shortly, and we've been successful. And you can see just at the bottom here, we have mined it, and that should be the same as this block hash here. Now, the only reason I was successful doing it in 10 seconds was because we knew all of the inputs. Now, because you've got this 2-hour time window, rather than iterate over a nonce, some people could change the time. So they just change the seconds, or they do different things. Or you can change maybe the transactions, so your Merkle tree slightly different. Different people have, or different mining pools have different ways of doing this. But what we've done there is, because we would have successfully mined the block, we would then send that through the mining transaction network, and then the next miner would see it, stop trying to mine their block with their set of transactions and their nonces, and start building on top of this one, because they've now got the block hash, and that then becomes the previous block hash. And so you can start to see how this chain sort of goes on. Now let's think about how you would unwind that. So I've spent 10 seconds there. I did 100,000 hashes in 10 seconds, as a matter of fact. And the current network is at a rate of 132 million terahashes every single second. So that's an incredible amount of hashing power. And this is where a lot of the energy usage and things come from. But the funny thing is that this is all balanced in and around a 10-minute time window. A block generally is produced every 10 minutes. And the reason for this is because blocks are every 2016 blocks, you rebalance the difficulty. And if you find that over the last 2016 blocks, it's taken on average 8 minutes to find a particular block, then the difficulty would increase to change that up till about 10 minutes. Vice versa, if the network found that it was taking 20 minutes on average to find a block, then the difficulty would drop. However, it wouldn't drop by 50%. It would drop by, I think the maximum is 12.5% that it would drop. Now, the reason I mention that is because that thing in itself can lead to problems. If you were to suddenly have this spiking of blocks, if a block on average took 1 hour, and miners do this, and they do this today, and the hash rate would come down, or the difficulty would come down, they would then immediately jump on top of that, and they would expend a significant amount of hash in that. And what you would do then is, rather than blocks every hour, you'd be receiving blocks every 2 minutes. So they'd be receiving block rewards every 2 minutes. And so it's very sort of selfish from that perspective. And you can really ruin a blockchain by doing that. And when we talk about forks, this is where this really comes into play. So how do these blocks propagate? Well, they're not sent over a normal network as normal sort of transactions are sent over. Miners send them over dedicated networks, and there's several of them. Fast relay network, fiber, or Falcon, for instance. And these are specialized in decreasing data transmission or dropped packets. And there's different algorithms such as extreme compact blocks or extreme thin blocks that help with that. Now, the reason is that if you've got miners positioned all over the world, you want to know, as soon as someone finds a block, you want to know straight away that that block has been found, because you're currently expending CPU cycles on something different. Somebody's already found it. You need to get that block. That's your previous hash, and start building on top of that to continue the chain. And so the data transmission needs to be as quick as possible. However, this can lead to things called race conditions, and there's current concern that mining could take place in one part of the world, and then you could sort of siphon off or segment off part of the chain, and suddenly things start getting tricky. And people can use selfish mining, where they won't propagate a block that's actually been found. They will build on top of it themselves, and then what that will do, and then they will release maybe a chain of 6 or 7 blocks, watching these other sort of part of the blockchain struggle along with maybe 3 or 4. And the rule is that the longest chain wins, or the chain with the most work effectively wins. And what could happen is then you could get a reorganization of blocks. and that can cause a problem. And all the transactions and all the block rewards suddenly they don't exist for this other group of people. They've lost all of their effective income, and you can start to bankrupt mining businesses doing this. And also you've orphaned blocks, so there's not a lot of happy people whose transactions now currently don't exist, and someone's gone and bought some digital goods, and they've got the digital goods, but the transaction suddenly disappeared from where it should have been. So this is quite a problem to tackle. We can see here the graph on the right is propagation delay versus block size. Block size is an increasingly important topic, because you can imagine the larger a block size, i.e. the number of transactions it's got in it, if it's got 1 million transactions in, then it's going to be a lot bigger, because a transaction is about 120 kilobits in size, let's say, and you've got 1 million of them, and you've got 10 minutes to get that block from A to B. And everyone has to see it, and then everyone has to start mining on it. Some blockchains propose gigabit-sized blocks, and those things are obviously not going to really travel. But there's a lot of work taking place to try and increase those sort of sizes. This can lead again to quite a lot of contention, because that's around scaling. Scaling is around how many transactions could you sort of output per second. Some blockchains say we'll scale at the base layer, we'll just increase the block size, but then what you get is propagation delays, so you've got to solve that. Then you get race conditions, drop packets, then you get miners behaving in a disincentivized way, just because you've changed this block size. So there's a lot of thought that needs to go into that. Generally, you don't try and change those things if you don't need to. You try and do something different. We can see here on this chart that block size in kilobytes, 100,000 to 10,000, there is a significant delay here, and these you may or may not be able to see it, but these are different locations around the world. So we've got Germany, the USA, Vietnam, and whatnot, each mining and trying to receive a block. And this data was found by doing it was like a one-day event, and they just sort of almost spammed the whole network and said sort of deal with it, and they sort of got this information back from there. So let's think about this so that's miners, and we can see how miners and block propagation and that type of thing can have an issue with regards to block size and whatnot. But then think about the users as well. If you run a node at home and you are receiving 1 million transactions every minute, that's a lot of bandwidth. That's also a lot of size on your personal computer. And what you might then get is a condition where a user cannot afford to run their own node. Which is a problem, because the whole point of this distributed system is for it to be distributed. You don't want these nodes running in the same Amazon, cloud system. So this is where things can get pretty crucial. So a user's node is all about validating blocks to ensure that the miners are being honest. A miner could easily, if they wish, take double the coin reward. There's no problem doing that. The only thing that's keeping them honest is the users and the rest of the network disregarding the block that they would create, and knowing that that block would be disregarded is the reason that they don't do that, because it takes too much time to do that, because they'd have to do the CPU mining, they'd have to and so on and so forth. But how does this whole thing then, from a transaction perspective, look? You don't get this one big block, and that block in itself is then sent to everyone every 10th minute increment. You have a continual flow of transactions. So if you were to run a Bitcoin node at home, you would have what's called a memory pool, and your memory pool may look completely different to another user's memory pool, because transactions have been propagating across the network, and they may have seen a transaction, and you may not have. Transactions that don't have the right fee can sit in a memory pool for forever, effectively, until they're dropped off, or until people seem to ignore them. I think that's about 15 days or 3 weeks or something it takes for that to happen. So you've really got to take advantage of this, because suddenly what might happen is there's a new block that's been found, but you don't actually have all of those transactions that block demonstrates in your memory pool, so you can't validate that whole thing. So you need to go and find those transactions from somewhere, and this is how the network then tries to pull those transactions in. But this begins the topic of this simplified payment verification systems. Block size, again, not running nodes on Amazon Web Services. Got a small detail in the bottom there that there was a large outage, I think only a couple of weeks ago. So if you're running all your nodes on one of these areas, then there could be something quite tricky. And it's pretty disingenuous as well to say you're running a sort of a distributed system on a blockchain node on a large cloud service provider. It doesn't seem to sort of jive with me in that sense. You can see here there's 10,800 nodes currently running. This was taken yesterday. This snapshot, a lot to sit in Europe and the US, but also China and Australia and so on. But anyone can fire up a node, and these are only the visible ones. There's a lot of nodes already on Tor as well. So there's probably, I think, overall. And these are full nodes that will communicate transactions to other nodes. You could run a node that doesn't communicate transactions, and there are about 150,000 of them as well. So there's quite a lot from that sort of perspective, and these obviously are all talking to one another. When you first initiate a node, you have sort of a seed, 8 seed nodes, and it will go to those other nodes, and it will try and take all the transactions from them. And then you will slowly get more and more connections. And I think the average amount of connections is 125, if you're lucky. So you can get all these different, and you only need one right connection. Even if the 124 are feeding you wrong information, if that one right one is the one that's going to be positive for you. So this leads to an interesting question. So I was going to put in a picture of the globe, but say, can transactions, what happens when the blockchain is sort of cut off? But it really leads to something more about, can it be intergalactic? You know, or could you have a payment system, say, or on Earth and on Mars? You know, I mean, Visa isn't going to necessarily do that sort of stuff. I don't know how that would pretty work, having a bank account and trying to transact in 2 different places when we eventually get there. But what we think about here is we then also think about, well, we've got a 10-minute block time, so we've got speed of light and the transactions. Would you be mining on both in both places? Could you take some Bitcoin over and then start transacting, have a block and seed off that block in a way? And this then you think about scalability. Scalability isn't just the number of transactions, it's about how you actually use the tool. And I'm not talking about 5 years, I'm talking about 100 or 200 years in the future. And this also leads back as well to shorter block times or larger blocks. For instance, block time in Bitcoin I've mentioned is 10 minutes. Ethereum, it's 15 seconds. So you can imagine that every 15 seconds, as soon as you get one wrong, you're sort of off the chain, and that starts to lead. That's something called uncling, and you suddenly you can build on an uncle, and it would still be accepted, or you'd still get some reward in some instance because the it's 15 seconds is so very fast. So I'm aware of the time, so we've got 15 minutes left, and we're going to be talking. So we're coming to the end of our sort of journey. We've spoken a lot about the software side of things, the hardware side of things. We're like a stone skimming across the surface of all of this. And now we're sort of going to get to the spirit. So can you duplicate a blockchain? So yes, you can duplicate a blockchain, but it isn't going to be the same blockchain. So I suppose the answer would be no, in that sense. When you try and duplicate a blockchain, it's very much like a GitHub repository in a sense, where somebody forks your code, and if somebody doesn't like what you've been doing, then they will go and work on this other code somewhere, and your repository either lives or it dies. On that sense, it could live and it could still have a few other people contributing, or this other repository could be super popular, and that would be doing super well. The one thing it doesn't get to take with it, though, is the original repo name, which is something that could also be very contentious, and there are ways that people try and do things around that. But in general, hard forks are generally not very good. Okay, hard forks are a very last option, because what you're doing is you're splitting the network and you're splitting the mining, which is the security of the network, into 2. So suddenly the network becomes a lot less secure. The target really isn't about the mining, though, or even the blockchains. It's about destroying the community, not the chain itself. The people that sort of do this don't really care about the chain. It's about trying to make sure that the community infights and then splits. And this is called something called a hash war, and we're going to see that in a second. And as soon as you start a hash war with someone, and it could be, I don't agree with what's going on in chain A, I'm going to fork it, I'm going to have chain B, and I'm going to get lots of miners to mine on it, and you get 50-50 miner split, and which chain's going to win, because they both want the same. They're both effectively doing the same thing. And you'd say, okay, well, why can't they live together in peace? Well, the issue is it's called a replay attack, and if you were to transact on one blockchain, that same transaction would occur on the second blockchain as well. And a lot of times people can do disruptive things by doing that. This tends to be now solved in a more sophisticated way, using futures markets to decide a split, funnily enough. Because these tokens have value, people will hook up a futures market, and they will try and assign a value to whatever future chain could be popular. And then people will then operate on that market. Miners will be watching that, and whichever one starts to come out popular, that's then, well, they'll start moving their hash power. They don't move their hash power and then let the market forces take shape itself. It's something else that's done, because there's too much riding on it. There was a fork recently in the Bitcoin Cash fork, which is a derivative in a sense of Bitcoin. There was a rogue developer. He just happened to have repo access and permission, was starting to do things that not many people in the Bitcoin Cash community liked. And this thing was giving himself 8% of the block reward for being the main developer. So people obviously didn't like that, but he had a few miners behind him. And the reason the miners were behind, because the miners knew that they could control this particular individual, and they could then start doing different things, maybe even taking the cap of 21 million Bitcoin off out of the code. And what happened there was the futures market suddenly started up. One of the exchanges said, okay, right, we'll put this. One's called ABCA, ABCB, and they just let that sort of fight it out itself. And in the end, the developer was sort of kicked off. The version they were running, the version or their repo was not used. Developers began to use another repo version. So this begins the topic of why you should really avoid blockchains with anointed gods or CEOs, because they're too easy to sort of subvert. And these things, there are very sophisticated actors trying to do this type of thing in the space. So, interesting question. Can blockchains grow old? Well, yes, they can, funnily enough. It's something that you may not think about. Is it even possible? How could a software in that way grow old? But they don't live in the same state forever. Blockchain rewards decline. So initially, it was 50 Bitcoin a block. Now every 4 years it halves, so it was 25. Now it was 12 and a half. It's 6. There was a block halving only this year, so it's 6.5. 6.25 Bitcoin, and in 4 years' time it'll be 3.125 or whatnot. And so this issuance is going to run out by about 2140. And so then what happens is the chain has to exist purely on transaction fees alone. Some people want to get there a lot earlier, some people don't. Pretty much by 2040 they'll be fighting over this very small increment. I think it's the very of the last sort of joint Bitcoin. So it's but I'd say about 15 years, transactions are going to have to really replace these block rewards. You can see here, the supply suddenly kits out, and we're around here. So we're virtually at the end of the supply, and the reward is coming down here. So in a way, blockchains do age because their state has changed. And come 2140, this blockchain won't be a young blockchain anymore. It will be an older blockchain, and it will be mature, and it will be having to exist on its own using transaction fees. So that's completely different. And miners will have to then mine from a transaction fee perspective and not a block reward perspective. And that changed a lot of motivations. This then begins the topic around transaction fees versus quantity of transactions, again, versus block size. So the smaller the fee, the larger the block, the more transactions are required, and so on. If you want your network secured, miners aren't going to mine it for free. So can you have two of the same blockchains? Well, they can have each of their own implementations. So, for instance, we've got here an example of hash war, and we've got one implementation ABC, another one BU, XT, Bcache, BSV, and so on and so forth. All these implementations are currently working on the same chain, but as soon as one of these implementations, and this is the sort of the nodes that are running, starts to act in a negative way, then a miner would pick sides with one, and they would sort of hash from that perspective. So yes, you can have two of the same blockchain in that sense, is that they can coexist as long as they follow the same rule set. You don't just have this one major implementation that everyone has to follow. You can have several major implementations, which is probably a bit better because you get more of a community from that sense. But this leads to the question around community: how are upgrades voted on? What happens if someone does go rogue? And then how are they agreed and deployed? Well, upgrades are decided in a not very sophisticated way at present. You just go around, ask, and we have a proof of support here. This is something called Taproot. So this is a Taproot proposal that's going through on the Bitcoin network. So Taproot is a protocol upgrade that's forward compatible. It's a soft fork. The main Bitcoin chain doesn't hard fork. It's going to expand Bitcoin smart contracting flexibility and privacy, and it's going to start masking these contracts as a regular Bitcoin transaction. So you can imagine different size transactions can identify different types of user. And the proof of support here was just simply a tweet. And this is a popular pool, Pooling. It's one of the largest, actually, 12.5 of global hash rate. Slush Pool have been around since 2011. They work a lot with the Bitcoin, and they've got a tweet as well. So you can also put it in the value field and so on and so forth. And so this is how currently upgrades are decided. It's something that the implementation don't really want to get involved in. They try and stay away from that. Because they don't want to be seen as these anointed gods. So they will just put a proposal, and it's up to the users to really figure it out for themselves. But they're always visible as Bitcoin improvement protocols. And users do get a say in upgrades. So just got a few minutes left, so we're coming to the end, so don't worry. So users running full nodes are key. During an upgrade in 2016-17, there was a contentious upgrade with about half the community around what's called segregated witness. And what was happening, very much like politics in this way, was that half the miners were saying, we'll allow SegWit to occur if you allow a block size to incur. And the reason they wanted a block size was because they could increase their fees. And the thing is, miners can game this, and they can create their own transactions, mine their own transactions, increase the fee set, but they would obviously get their own fees back, and suddenly the fees have gone up for everyone. So block sizes don't actually solve that particular problem. This SegWit and block size was called a New York agreement, and it was seen as a gentleman's agreement. And the view was that one half went back on that, and the other half wanted something else to happen. So this was actually the lead to the split between the Bitcoin Cash and the Bitcoin people. And we can see here that generally the users, they didn't want a block size increase. Increasing block size even once means you can do it again. And as soon as you start down that road, why 1 megabit, why 2, why 4, why not 12, why not 16? Oh, we've got a bit of a problem. Why not even 24? And that starts to stop people using full nodes at home. You wouldn't be able to run a full node at home in a suitable way because of all the transactions you'd be receiving. And it also leads to miner, which in itself leads to centralization and miner centralization as well. So in this period, what we did was we did something called user activated soft fork, where we switched implementations. And we just said that you can either follow us or you can mine on a chain that is just not going to be used. And you can see here that this was the implementation, and this was the group of people. This was the miners signaling for just SegWit without the block size. And as soon as they could see there was people that were wanting to use this chain, then suddenly the activation went up and the block size wasn't implemented, and segregated witness was implemented in that sense. So there's lots of different things about this. So I've just seen Chris, I probably missed that question in there about bugs getting exploited. I'll come back to that at the end. So I've come to the end of my presentation. I'm going to answer Chris's question, and then we're going to feed some chickens. I've got some lightning. I've got some things here. It's pretty dark out there, so what I'm going to do, you're going to see my screen drop off, and we're going to come back on, and we're going to see how this. And I'm going to share my screen in a second. Okay, so I'm going to stop sharing, and then I'm going to share again. So this is really cool. So this is just a group of chickens. So this is something called the Lightning Network, and you can take whatever wallet that you're wanting to use, and we're going to use some Lightning, which is a second layer technology, and we're going to click to feed these chickens. So I'm just going to scan this. You'll see me scan something. Okay, it's 50 satoshis, which is less than a penny. And you're going to see this chicken feed open in a second. So yeah, loads of mealworms, and these chickens get fed by particularly nerdy users wanting to feed chickens using a digital token. So that's pretty cool in itself. So I'm just going to come off that, and I'm going to jump back onto the slide again. Okay, so that was the screenshot was from earlier on, so it wasn't actually nighttime, it's daytime now. So what we've done there is, although it was a very quick demonstration, and you can always go through it again on the video, I used second layer technology, Lightning Network, to pay an automated thing in whatever country, wherever this is, to feed some chickens. And the interesting thing was that, yes, me as a human, I made that, but there's no reason for me as a human to do that transaction. As a matter of fact, with digital technologies of this nature, there is no reason why humans have to exist in the scenario whatsoever, in a sense. And this can lead to interesting activities about machine-to-machine payments, how that operates, and what sort of paradigms that may bring. A machine is never going to have a MasterCard, but it can always have a digital wallet. And so that to me is super interesting. So what have we covered? Well, we've done a whirlwind tour of the mind, body, and spirit of blockchain technology. We've skimmed over the surface like a stone, and there's so much more to go, and so much more to jump in. But I'm going to leave now with one of my favorite videos, and this is a visualization of the Bitcoin Hub, the Bitcoin repository being developed. And this is Satoshi Nakamoto developing Bitcoin on his own in the early and later parts of 2009 and getting his first contributor. So what I'm going to do is I'm going to answer the question by Chris. How often do these bugs get exploited? Well, not very often. So the exploitation of these bugs is something that you can see, because it's going to be something around the only thing that's going to happen is you're either going to get an extra block reward, a transaction won't go through, or you're going to see some sort of denial of service request going in. On the CVEs that are published, you can go back through all the transactions on, let's say, one side of the chain and transactions on the other side of the chain, and you can do a comparison, and you can say, okay, look, there was one double spend here, and so on and so forth. But no, not that often. Here we've got Laszlo, the first person. You'll have heard of the Bitcoin pizza, 10,000 Bitcoin for a £25 pizza, and I think it was a guy in the UK or someone did that. And so everyone, it's been really great speaking with you. I've really enjoyed presenting. I'm really enthusiastic about this technology. So have a great day, and look forward to speaking to you again. Thank you.